We're going to use number 2 to intro the idea of maxima and minima, the plural of maximum and minimum. And as you think about the term absolute minimum, you think about minimum and you think, the least, and absolute being, when you compare it to everything. And that's exactly what the absolute minimum would be. And keep in mind when you're talking about minimum, when we talk about a function, we talk about how big it is or how small it is or how one part of it compares to another, we're talking about the outputs, the y values. Those are the things that we're interested in. The inputs are a little bit mundane. They are just the inputs. They don't have anything terribly interesting about them. You put them into the function, what comes out is really what you're interested in. You put in 1, 2, 3, 4, and whatever, and then you see what happens. So when we talk about the biggest value, the maximum, or the minimum, the smallest value, we're talking about the y value, the output. So when we look at this function and we look at how big it is, how tall it is, or how small it is, we're talking about the y value. So for the absolute minimum, we're looking at the overall smallest value, and that looks like it's a. It's the furthest down. It's the biggest negative number compared to everything else on the graph. It is absolutely the minimum. So there you go. There's the absolute minimum at a. Now, if we talk about the absolute maximum, we look at E, it looks pretty big. B is even bigger. And then we look at G, and it looks a little bit higher even than B. Now, the strict definition of the maximum, and it is very much similar for the minimum, is that the maximum would be some f of c, so that f of c is greater than or equal to all other, it's greater than or equal to f of x for all x on I. Okay? So, first of all, we're talking about this function, f, and we're talking about it on I. I is just an interval. The interval from here to here. Right? So we look at it in this little window, and we look on this little window, including the ends, right? This closed interval. What's the biggest, what's the smallest? In that interval we call I. So it looks like G is the biggest, except the only thing is this open circle. G is like not actually a defined point. Okay? So if this were, 5 or something, the function actually is not worth 5. It doesn't actually get there. There's an open circle. But then you might say, well, it's still the biggest, because it's got these values that are really close to 5, and so the maximum must be somewhere in there. There must be some absolute maximum number. But as it turns out, there couldn't be, because say you want to get really close to 5, and you say, well, then the maximum is like 4.99. That's just close enough. It's the maximum. But the definition of the maximum is that this f of c, this value, is greater than or equal to all other y values that you could think of on this interval for this function. But if you pick 4.99, I'll pick 4.999. I'll get even closer to 5. And then if you pick 4.9999, I'll just throw another 9 on there, and I'll be even closer. And I'll always find a number that's bigger than the number you pick. Or vice versa. You could be picking the bigger numbers and besting me all the time. But the point is, you cannot find a maximum, an absolute maximum value. So it turns out there is no absolute maximum for this graph on this interval. Um, but there's all these other values like B and E and D and F, right? They look like maxima and minima, and they are. They just aren't the absolutes. Um, B is, like, right up here at the tippy top is the maximum for this little section right here. Okay, so if we were to cut down this into this little interval, that'd be the absolute maximum on this interval. But on this entire interval here, it's not the absolute, but it is a maximum in its little area. So we say it's relative, right? In this relatively in this area, it is the maximum. So yeah, relative. It's a relative maximum. And likewise, D is a relative minimum, relative maximum here at E, and relative minimum at F. Okay, because we can see that they're all defined at those points, and right at the very top you find the maximum for this little area and the minimum for this little area. Okay, so just do something for a moment. Okay. Now let's do like an actual problem. Let's talk about critical values. A critical value, in this case, say C is a critical value. It's a critical value if, let's actually go back. C is a critical value if f of c, or f prime of c, the derivative at this point c, is equal to 0, or f prime of c is undefined. Okay. For instance, say 9. If we go like this, we look at this graph. We're going to look for critical values. And I'm looking for whether either the derivative is 0 or undefined. And we should be able to see right here at the very tip top, the tangent line. We have positive slopes here and negative slopes here, and right in the middle we'll have a slope of 0, which is a horizontal line. And so f prime at that point is 0. And that point on this one is 2. So 2 is a critical value. And for number 10, actually it goes like this. It goes through the origin. And so right here at the origin, we've got this horizontal tangent. F prime is equal to c there. So at 0, we have a critical value. And 11. We've got 2 as a critical value because the derivative is undefined. Remember, at a cusp or at a point, there is no derivative. It doesn't exist. It's not defined. Because I could draw all sorts of tangent lines through this one point, and to have a derivative, you have to have the tangent line, the slope at that point. But here and here, we have slopes of 0. So at 1 and 3, we have tangent lines of 0, and so we have critical values. 0 is a critical value here. 1, 2, and 3 are critical values here. Also, since we have open circles here, you don't have a derivative at this point either, because the function does not exist. Well, see, if the function doesn't exist, the function's not there. There's a hole there. There's no derivative to speak of. So if the function is not defined, you couldn't have a derivative, and so there is no critical value. It's just not there. Okay. And for 12, Actually, I should have drawn that a little better so that this actually levels off. It gets kind of flat. So this happens to be 2, and this is 4 here. And what you'll notice about this, and also about this one, is that we do have a slope of 0, but we do not have a maximum or a minimum like a lot of times we do, like here. Here there's a slope of 0, and there's a maximum. Okay? So that's something that we want to talk about with our next theorem, and that is basically to say if there is a max or min, then it happens at a critical value. So if there's a maximum or minimum, it happens at a critical value. Okay? So it's important to understand that this only goes one way. This implication only goes one way. That's to say that if, let's say, you find an extreme, a maximum or a minimum, that implies that that extreme, when you've walked along the graph and you've come to this extreme, you will find yourself at a critical value. But does not necessarily mean that if you go to a critical value and look at the function, it does not necessarily imply, well, it doesn't imply that there's a maximum or minimum. Okay, there may be one, but it's not implied by being at a critical value, which we see here. We're at a critical value, the slope is 0, but we're not at a maximum or minimum. And so that's an example of that not being the case, that you're at a critical value and that you find a maximum or a minimum. But it is helpful to look at the critical values, and maybe you have a maximum or a minimum. And you're definitely only going to find these extrema at a critical value. Okay. And if you don't believe it, you have to, because it's a theorem. You don't mess with a theorem. Let's start with number 15. 15, we just want to find critical values. Okay. And this is for t less than 3. They're always going to give us some interval. This interval apparently goes on forever in the negative direction, and it stops at 3. Actually, it never gets to 3, but it gets really close. It's strictly less than 3. And so we're looking for critical values, and if critical values are where we find derivatives that are 0 or undefined, well, first we'd have to find the derivative. So let's find that derivative. This one's a little trickier than it might look. First, we're going to use the product rule. And the product rule would tell me start with the derivative of t, 1, and then times the square root of 4 minus t. Then add to that t times the derivative of this. Okay, this is 4 minus t to the 1/2. That's going to help me use the power rule. That's going to be 1/2 times 4 minus t to the negative 1/2 when we subtract 1 from the power. And then we notice, oh, the outside function was the square root. The inside function is actually 4 minus t, so I need to use the chain rule to find the derivative of the inside, and the derivative of 4 minus t would just be negative 1. Okay, so we've got the square root of 4 minus t minus, let's see what this cleans up to be, minus t, right? And let's say like t over 2, for this part 1/2 times t would be the same as t over 2. And then that's times this thing. Well, the negative means that this is like actually in the denominator, and the 1/2 power is the square root, so this is actually in the denominator as well, the square root of 4 minus t. So we've got the negative t over 2 times the square root of 4 minus t. And let's put these together, and to put these together, we're going to need a common denominator. This, of course, is going to be that denominator. And over here, we're going to multiply by 2 times the square root of 4 minus t over 2 times the square root of 4 minus t. So our denominator, when we get done, is going to be 2 times the square root of 4 minus t. When I multiply this by 2 times the square root of 4 minus t, well, first I'll have t, or 2. And when I multiply this basically by itself, the square roots will cancel, and so I'll have 4 minus t. And then I will have a minus t up here because I subtract this t. Alright, so let's distribute and combine like terms. This is going to be an 8. Then I'll have a negative 2t and a negative t for a total of negative 3t over 2 times the square root of 4 minus t. Okay. Now, we're looking for critical values where the denominator, or not the denominator, the derivative is 0 or undefined. So if this, the derivative, is equal to 0, if I multiply by the denominator on both sides, I find out really all that matters in a fraction is if the numerator is equal to 0. If that's equal to 0, then the whole fraction is 0. Okay, so I'll subtract 8, divide by negative 3, and t is equal to 8/3. And that is less than 3, so it's on our interval, so it is a critical value. Alright, now we're looking at the denominator being, or the derivative being undefined, which would equate to the denominator being 0, since we're looking at a fraction. That's one possibility. When the denominator is 0, then the derivative is undefined. So we'll divide by t, or t2, divide by 2, still 0, square both sides, still 0, and so t would have to be 4 in order for the denominator to be 0 and therefore the derivative to be undefined. But our interval is for numbers that are less than 3. And 4 is not less than 3, so it's not really valid. One other possibility is, undefined things happen when the square root is being taken of a negative number. But in order for that to happen, t would actually have to be greater than 4. You have to get past 4, like 4.1, in order to take this 4 and be able to subtract enough to take it into the negative realm. So the only problem with that is still our interval is for values less than 3. And if we go past 4, that's certainly not less than 3. And so that's not going to work. So our only critical value on this interval is 8/3, where the derivative is 0. Okay. Now, 16. Okay. So first we have to find the derivative. That's going to be the quotient rule. You can look up the quotient rule if you have forgotten. Let's see, we have a 4x squared here and a negative 8x squared here. So negative 4x squared altogether plus 4 all over x squared plus 1 squared. And so now we're looking for critical values. Critical values where the derivative is equal to 0 or is undefined. So let's start with the derivative being 0. I apologize for you. Let's see. There's no defined interval, so the interval is anything. Any x will work. So here we go. Negative 4x squared plus 4 is equal to 0. This will be the numerator is 0, and therefore the derivative is 0. So negative 4x squared equals negative 4. Divide by negative 4 on both sides. X squared equals 1. and x equals plus or minus 1. So there are a couple critical values, plus or minus 1. Also, if the denominator is 0, then the derivative is undefined, and so we have a critical value. So take the square root of both sides, and subtract 1 apparently all at the same time. We take the square root of both sides, we'll get x squared plus 1 equals 0, and then we subtract 1 from both sides, and we wind up with this. And take the square root again. But the problem with this is that this is not a real value, so you're not going to look at the graph and find the square root of negative 1. And so this isn't really a critical value. At least it's not a real one. So we're good there. Nowhere is this derivative undefined. But we found a couple critical values there at plus and minus 1. Okay, let me start with 19. Now we have a little bit of extra, well, I guess we have the general directions of find absolute extrema of the function on the closed interval. Okay, so looking back at number 2, remember that absolute extrema happen either at maximums or minimums, or maybe at either end of the interval. And so we're going to test all of those points, right? In our head we're thinking there's this function, and there's this interval, and there's this, a graph in between. I'm not sure what it looks like, but either I have an absolute maximum or minimum here, an absolute maximum or minimum over here, or there's a mountain peak or a valley low that is actually larger than or less than these endpoints, and so our absolute maximum or minimum might be somewhere in the middle, and so we have to figure all of that out. And we will find out how very soon. And this is going to be between negative 1 and 2. Alright, so first let's just call this 6 minus 2x. May as well. And then we find the derivative, because, keep in mind, we're thinking either the maximum or minimum is over here, or somewhere in the middle, and we have this theorem that says if there's a maximum or a minimum, then it's going to happen at a critical value. So we're going to find critical values for this function. And, whoa, what a derivative. And so is this derivative ever 0 or undefined? No, it's never 0, it's negative 2, and it's always defined as negative 2. So we don't have any maxima or minima, and that makes sense because this is a line, right? A line with a slope of negative 2 and a y-intercept of 6. So our absolute maximum and minimum are going to be on the endpoints of the interval. So let's put in negative 1 and see what we get out of the function, right? How big or small is the function at negative 1? F of negative 1 is, let's use this here, 6 plus 2, right? Negative 1 times negative 2 is positive 2. And so that's 8. Let's look at the other side of the interval. That'd be 6 minus 4. And that's 2. Here's your absolute maximum and your absolute minimum on that interval. Let's go to 28. On the interval negative 2 to 2. And remember again, we're thinking in our heads there is this function, this one, and we're going to look at it from here to here on this interval, and something's happening in between, we're not sure what, and we're thinking we got a maximum in here, or maybe it's somewhere in the middle. If it's in the middle, it happens at a critical value, so let's find those critical values. And to find those, we need to find the derivative. using the quotient rule. Let's clean this up some. Negative 4x squared and a 2x squared. So 2x squared minus a 4x squared is negative 2x squared, and plus 2, and we distribute that 2 over x squared plus 1 squared. So now we've got a pretty cleaned up looking derivative, and we want to know the critical values, so we need to know when the derivative is 0 or undefined. So it's 0 when this is 0, and so x squared is equal to 1, and x is equal to plus or minus 1 when we take the derivative of both sides, or when we take the square root of both sides. And that is on the interval, so these are possibly some maximum, a maximum or a minimum. Okay, so let's keep that in mind. Then let's find other critical values by finding when the derivative is undefined. And of course, this is not a valid critical value because this is not a real number. So now we have some candidates for maximum and minimum, either here, or here at -1, or here at +1, or all the way out to +2. So we're going to look at all of these values. F of -2 is 2 times -2, that's -4, and then we have -2 squared, that's +4, plus 1, that's 5, so we have a 4 over 5. Negative 4 over 5. Okay. How about f of -1? I'm just going in order of least to greatest. 2 times -1 is -2. Then we have a 1 plus 1. That's 2, so -1. Then f of +1. That's a +2 and a +2. So that's a +1. And f of 2 is 2 times 2, that's 4 over 5. That's +4 fifths. Okay. We're just looking at what is our maximum, what is our minimum value. Well, here's the biggest one. So there's your absolute max, and here is your absolute minimum. It's 4/5 and -4/5. They're not quite as maximum and minimum as 1 and -1. Okay. Let's try 29. Remember, our overall goal is to find the absolute minimum and absolute maximum, and either, let's see, it's happening from 0 to 1, so the left side of our interval is here, the right side is here at 1, something's happening in between, and either our maximum is here, or somewhere in the middle. If it's in the middle, it happens at a critical value, so we're going to find those critical values. H prime of s is equal to -1 over s minus 2 squared. Whether you use the quotient rule or you write this as s minus 2 to the -1 and take the derivative using the power rule, you'll find that this is what you wind up with. So we're going to find critical values. That's where the derivative is equal to 0. Well, it'll never be equal to 0 because the denominator, or the numerator, will never be equal to 0. It's always -1. So it's only going to possibly have critical values if the derivative is undefined. So s equals 2 is a critical value, but you know what? 2 is outside of our interval, so that doesn't really matter. This is not going to count. So it comes down to 0 and 1. So h of 0, we're definitely going to find our absolute maximum and minimum here unless we find that it's undefined or something. So we put 1 over 0 minus 2, that's going to be a negative 1/2, and h of 1 is going to be negative 1. Yeah, so here is our biggest value, so this would be our absolute maximum, and our absolute minimum is at negative 1. Okay. Alright, let's try number 60. So a retailer has found that it costs him this much, or her. 300,000 over x. Okay. We'll find out the significance of this interval here in a second. Okay, so it costs him or her this much to order and store this many units of product. Right? And so we'll kind of assume that a truck can bring all of this stuff. He's going to order, X amount of units, and all that stuff's going to come on a truck, one truck. So it costs this much to call the people and have them deliver all this stuff on a truck, and then for him or her to take all the stuff and store it for a while. It costs this much. It's a function of how many units they order. So the delivery truck can bring at most 300 units per order. That would be the meaning of this interval here, right? You're going to order at least one, and you're going to order at most 300 units, because that's how much the truck can carry. So find the order size that will minimize the cost. Could the cost be decreased if the truck were replaced with one that could bring at most 400 units? So, we all know the idea that if you order lots of something, it kind of costs less in the sense that each thing costs less, per unit. That's why people shop at Costco. That's why Costco charges you, 30 cents for 2 gallons of mayonnaise, because you buy a lot of it all at once, and it costs those people less to put a bunch of mayonnaise in one plastic container and sell it to you in that amount than to sell you a bunch of little ones. So less per ounce, let's say. So what we're asking is, this is a function, and on this interval there's got to be some maximum and some minimum. And then we'll look at what is that minimum and can it be improved. Okay, so either it's the cheapest to order 1, or it's the cheapest to order 300, or it's the cheapest to order something in the middle on this interval. So let's find out. First we need to find the derivative. So c prime is 2 plus, let's see, actually let's think of this as 300,000 times x to the negative 1, right? So this is in your mind. So we use the power rule here. 300,000 over x squared. Alright, so where is this equal to 0? Where is this equal to, undefined? I don't know that that's proper to say, equal to undefined, but I said it. There's no taking it back now. It's on the internet. So where is the derivative equal to 0? Okay, well that's where this is equal to that over x squared. And so that's where x squared is equal to 300,000 over 2, and so, okay, so x is equal to 387. Oh, excuse me, 387.298. Okay, so if you ordered this many, well, something. This is a critical value. This is where the derivative is equal to 0. So if we were to look at the graph, then over here at 387.298, we might see a minimum, we might see a maximum, we might see a leveling off like this or like that, right? That's what's happening here at 387.298. But for this first part, we can't actually worry about this number because it's outside of this interval. So on this interval, what's the cheapest? It's either to order 1, which is doubtful, or to order 300. Okay, so let's find out. So is cost for 1 unit, just using this notation to see that we're putting 1 in here, is equal to, let's just throw the numbers in, not worry about writing it all down. So 2 plus, okay, this is silly. This is going to be 300,002. Okay. Now C of 300, that would be so 600 plus 300,000 over 300. That's 1,600. That's much better. This is 1,600. It's okay. So 1,600 rather than 300,002. So that's much better. So on that interval, ordering the maximum is the best. You know, shouldn't have used the word maximum. Ordering the most units he possibly can fit on a truck is best. Then the question was, what if the truck could hold 400 things? That's part B. Right, this is part A. So ordering 300 is best. Part B, the question is, if it was increased to a 400 units per truck, then would that be better? Well, what that does is that it allows us to include this value as a possible minimum. So let's find out what that is. C of 387.298. And that should have been okay, so let's put that into the function. That's times 2 plus let's just round to 387, and if we do the calculations for 387, which is going to give us, you know, a yes or a no that we could tell the book, it gives us about 1549. So that is less than 1,600, so if we could carry as many as 400 units, we could carry 387 units, which is the optimal. That is that's the number that you want to carry on the truck to minimize your cost. So the answer would be yes, that'd be best. Alright, hope that was helpful.